Now we talk about the derived functor x. So again, remember that if these are co-chain complexes, so co-chain complexes means the indexes within each of these complexes are increasing. So for example, in this curly A, we would have an entire complex, in fact a co-chain complex, where we will go from A0 to A1 to A2 and A3, so on. In curly B, we will go from B0 to B1 to B2 and so on, and similarly with C. So a cohomology theorem says that we get cohomology groups like this for this co-chain complex. So we need to do the same for X groups. So you start with a given sequence of R modules A, B, C, and then you apply this functor home to it. So G is an R module, you apply this functor home. So first you do a projective resolution of G. So notice that we are using a contravariant functor, so you have to do a projective resolution. And the projective resolution of G which we use is standard P0, P1, P2 and so on, just like in the Tor example, but I will just write it down for sake of completeness. You have P0, then you have P1 and so on coming into it. Now you apply this functor to it. To this, you delete G, you apply home dash A. So this is a contravariant functor, so the arrows will reverse. So this is what we will get. You have delete G, you get 0 here. Similarly, you apply a home B to it. This is again a contravariant functor, so the arrows will reverse. Then you have this here. Now you have exact sequences right here because each of these PNs is projective modules, so you have exact sequences here. So since you have these exact sequences here, what you have is a complex. So you have a complex A, B, C. So this is complex. This is A. Go to this entire stack is B. This entire stack is C. So this is a co-chain complex. Now notice that we are going from P0 to P1 to P2. We are going from Pn minus 1 to Pn, Pn minus 1 to Pn. So we have a co-chain complex. So you just throw in the cohomology theorem. Instead of these cohomology groups, you write X. And you start from 0, precisely because you have zeros right here. This group is ending at 0, so there is no minus 1, minus 2 going on. And you get a series of X groups, and the notation is instead of curly A you write A comma G, instead of curly B you write B comma G, instead of curly C you write C comma G. And that is pretty much it. So the story is you have to have a complex from this short exact sequence by application of this thing called home. Now sometimes to make a complex, people also use something called Horseshoe Lemma. Which is again a useful trick, but the fact remains that it does not matter what kind of projective resolution you use, because any two projective resolutions you might use will be homotopic to each other, as we have shown before. So the fundamental principle is this: you need to come up with some kind of a complex here, or you need to argue about existence of some complex like this here, and then this existence of complex will give you X groups automatically. So this existence of complex has to be tied up to this functor home. So if you are able to tie these two up, that's it. Then you will automatically get X. Similarly, you take this complex and tie up with tensor product and you get Tor.